Hello pre-calc students. Today we're doing graphs of polar equations. So equations whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. So example 1, we're going to do the point plotting method. And what we're essentially looking at for the equation r equals the sine of theta is all points, or r equals to 4 sine of theta, is all the points that are 4 times the sine of the angle that you face away from the center. And you're going to do that for every single angle that you can face in the circle. So let's start out when theta is 0 radians, alright? When theta is 0 radians, right, the sine of 0 is going to be 0, right? So when you're in radians, the sine of 0 is 0. So 4 times the sine of 0 is 4 times 0, which is going to be 0. So we have theta is 0, r is 0. And so when you're facing 0 radians, you move out 0 units, so you just stay in the center. Now, when theta is pi over 6 radians, you can look at the sine of pi over 6. The sine of pi over 6 is 1/2. So 4 times the sine of pi over 6, which is 1/2, is going to be equal to 2. So the sine of pi over 6 is 2. So now, this is for all angles, but we're just picking specific angles. When you're facing pi over 6 radians, right, you're going to be going 2 units out. Pi over 3, same concept. The sine of pi over 3 is root 3 over 2. So 4 times root 3 over 2 is equal to 2 times the square root of 3, and 2 times the square root of 3 this will be equal to 3.46. So this is going to be equal to 2 root 3, which is approximately equal to 3.46. And we can keep on plotting points. The sine of pi over 2 is 1. 4 times 1 is 4. The sine of 2 pi over 3 is also 2 root 3 over 2. So this will always also be 2 root 3, which is approximately equal to 3.46. The sine of 5 pi over 6 is also 1/2. 1/2 times 4 is 2. The sine of pi is 0. And so 4 times 0 is 0. So when we look at all these rotations, we're facing pi over 6, 2, pi over 3, about 3.5, 1, 2, 3.5, pi over 2, 4, 2 pi over 3, 3.46, five pi over 6, 2, and then pi, we're back at 0. And as we are facing the negative directions, the negative angles, the sign, the value is negative. So even though you're facing the opposite direction, your outcome becomes negative. So you just end up going back to where you started. So you end up getting a circle that's going to look as such. And we can see the circle when we graph it in our calculators. Go to mode, go to polar mode, and let's plot 4 times the sine of theta. Make our window go from -6 to +6 for both the x's and the y's. Let's graph it. Okay, so this is our angle that kind of matches up with this polar graph right here, a polar circle. So if a polar equation involves only r is equal to a times the sine of theta, or r equals to a cosine of theta, then your graph will be circle. So let's describe the directions that our polar circles can take. R is going to be equal to plus or minus a times the cosine of theta, and this is going to be indicate x-axis symmetry. Or r is going to be equal to plus or minus a times the sine of theta, which will indicate y-axis symmetry. Alright, so we're going to go plus a on the right, minus a on the left, plus a up, and minus a down. So this indicates the symmetry for polar circles in the form plus or minus a the cosine of theta and plus or minus a times the sine of theta. Moving on. Let's clear annotations. We're going to have our test for symmetry. If our test is r, theta pi minus theta, or negative r, negative theta, we can replace theta by pi minus theta. There's symmetry with respect to, so that what that means is with respect to you will have, so if you have this test, you can have symmetry with respect to the y-axis, otherwise called when, you can call the y-axis when theta is equal to pi over 2. Think about that one. When you have r, negative theta, and negative r, pi minus theta, you can replace theta by negative theta. Then your symmetry is with the x-axis. We can also call the x-axis the polar axis. Alright? And when you have negative r comma theta and r comma pi plus theta, you can replace r by negative r. So then you have symmetry across the origin slash the pole. So let's put these definitions into use. These three tests are sufficient to guarantee symmetry, but they're not necessary. So, if a graph fails the symmetry test, it doesn't mean it's not symmetric. But if it passes the test, it must be symmetric. Here are our quick tests. R is equal to the sine of theta. That's going to be symmetric with respect to the x-axis. R is equal to g times the cosine of theta. That's going to be respectful with respect to the y-axis. And so those are our two quick tests. So now I'm going to go into analyzing some of the polar graphs that you may be exposed to in the pre-calculus course. First shape that we're going to look at is the cardioid. And if you haven't seen a cardioid or a limicon before, we're going to graph it in a second. But a cardioid is in the form r is equal to a plus b times the cosine of theta, and r is equal to a plus b times the sine of theta. And the type of shape is depending on the ratio between a and b. If the absolute value of a divided by b is equal to 1, then the shape is going to take the form of a cardioid. If the ratio of a over b is greater than 1 but less than 2, then the shape that's going to take place is called a dimpled limicon. If a over b is greater than or equal to 2, then our shape is going to be called a convex limicon. And if a minus b and a plus b give axis values that means a is also an axis value. Alright, so now that we have the pattern explained, let's dive into some examples. A. R is equal to 2 plus 2 times the cosine of theta. So in this shape, we're going to have symmetry with the polar axis. And a ratio of a over b, which is going to be equal to 2 over 2. It's going to be equal to 1. We have a positive cosine. Just going to be making you're moving right. And so you have a minus b equals 0. A plus b equals 4. Remember, a is 2, b is 2. And a is equal to 2. So that being said, let's graph the cardioid. And we can use our calculator and Desmos to do this. So we have r is equal to 2 plus 2 times the cosine of theta. When we graph it, we have our cardioid. Let's look at this in Desmos as well. Well, we'll graph it first. So, graph in Desmos, we look at our values, okay? A plus B is 4. So we're going to go 4 in this direction. Then we're going to go up 2 and down 2 on the x-axis. So we're going to have a point at 4, 0, a point at 0, 2, a point at 0, negative 2. And then drawing the shape of a cardioid, we would go back and forth like such, drawing the cardioid. Now obviously your drawing doesn't have to be picture perfect, but if we clear annotations and show it on Desmos, we can do the equation r equals 2 plus 2 times the cosine of theta, and we have our cardioid right here. We have the critical values of 4 in this direction, 2 on the y, 2 as a y-axis value, and negative 2 is another y-intercept. Alright, let's move on to part B. 2 minus 2 times the sine of theta. Graphing this, you're going to have now, hopefully you can see on the graph, symmetry with the y-axis. Your ratio is going to be, once again, a over b is equal to 1. You have a negative sign, so it opens down. And a minus b is equal to 4. A plus b equals 0. And a is equal to 2. So we're going to have our equation. Zero, 2, negative 2, and negative 4. Drawing the cardioid. Once again, this will rotate towards behind the 2 points. And it should make a heart-like shape. C, r is equal to 3 plus 2 times the cosine of theta. You have your polar axis. Symmetry of the polar axis. You have a ratio of a over b, which is 3 over 2. So this is a positive cosine, so it's going to open right. And we know that a minus b, remember a is 3, b is 2, so a minus b is 1 a plus b equals 5. And a is equal to 3. So in this case, we're going to have a point at -1. We're going to have a point at 5. And we'll have a point going up and down of y-intercepts at 0, 3, and 0, -3. And this is what a dimpled limicon will look like. Remember, this is a dimpled limicon. So drawing the polar graphs, we would move out to this point, come back to this point, and then have the limicon dimple in. And we can use our calculator to draw the polar graph. Y is equal to 3 plus 2 times the cosine of theta, and you kind of see the dimpled limicon curve here. That's C for problem D. We can have R is equal to 5 minus 2 times the sine of theta. Here, it's sine of theta, symmetry is going to be the y-axis. Theta is equal to pi over 2. And we have a ratio of A over B is 5 to 2. A is 5, B is 2. This is going to be a negative sign, so it's going to open down. A minus B, that's going to be 5 minus -2. Remember, that's going to be equal to 7. A plus B is going to be equal to 3. And A is equal to 5. So A is moving 5 units left, right. A plus B is moving 3 units up. 7 is going to be 7 units down. So plotting our points, we're going to be having, starting from the origin, 3 units up. 1, 2, 3. Starting from the origin, 7 units down. 1, 2, 3, 4, 5, 6, 7. And now we're going to move 5 units to the left and the right. So in order to graph this, I'm going to have to change my window, so that instead of my maxes and mins becoming -6, they'll have to become -8 and 8. -8 and 8. And when I graph this, I'm going to do 5 minus 2 times the sine of theta. Graphing the equation, it does look like it hits all of these important points. Drawing the circle, or not the circle, the convex limicon, you could say. It's going to look something like that. So this is a convex limicon. Alright, clearing annotations. We have pure limicon. Pure limicon is going to have, let's describe our pattern. If the absolute value of a over b is less than 1, you will have a inner loop limicon. If a over b is equal to 1, you will have a cardioid. Cardioid. And if a over b is greater than 1, you have a dimpled, or it's dimpled or convex. It's going to be dimpled or convex. So let's get into some examples. Here I'm going to start with graphing. R is going to be 1 minus 2 times the cosine of theta. And so this should show us points. Let me change my window back to do everything in range of 4 now. Negative 4, 4, negative 4, and 4. So there's our inner. So let's look at this thing. This is our shape, the symmetry. It's cosine. This will give us some polar axis or x-axis slash polar axis symmetry. Our ratio is a is 1 and b is 2. So once again, that makes this an inner loop limicon. We have a negative cosine. Which means this polar graph is going to open left. And we have, let's look at our a values. A minus b is equal to 3. So 1 minus negative 2 is equal to positive 3. 1 plus negative 2 would be equal to negative 1. And a is equal to 1. That's going up and down. So let's plot our points. We would have a point at 3. We would have a point going, if we're facing right, we'd move 3. We're facing it opens left, not right, so you would be facing these directions. You are facing left for a minus b, so you move left 1, 2, 3. You are facing right for a plus b, and then you move backwards 1, so you walk back 1. So you're facing this direction, facing towards that positive 6, and you walk back 1, bringing you to the point 0, negative 1. And then you're going to be going up and down 1 to create this shape. And now, for this inner loop limicon, what you kind of have to do is you have to go draw the inner loop so you're coming it from the opposite directions. This will create an inner loop like so. I'm going to go from this loop and loop outward towards my inner loop, and then close off the loop and loop back to my second point, and then create my inner loop limicon. So the whole thing, different aspects of the limicon. You have this part of the loop, this part of the loop, and then you loop around between the three outside points as such. Okay, so that's the inner loop limicon. Let's look at graph B. You have a symmetry. Theta is equal to pi over 2. The ratio is 1/2 is less than 1. So it's going to be, the ratio is going to be positive. So you're going to have a positive sign value, which means you're going to move up. A minus B is going to be equal to -1. Alright, so normally that would be facing down, but now you're facing up. A plus B is going to be 3, so you're moving 3 up, and then A is equal to 1. So we're going to move up 1, up 3, and then be left, right, 1. And creating our inner loop, we would go from the outside in, create that inner loop. Let me increase the thickness here. Create an inner loop like such, and then move around, create your limicon curve. Alright. So remember, that's looping in and out. And you have your points that you are looping around right here. Those are your critical points. Clearing annotations. We're going to move to this video right here. Or sorry, this graph right here. C, 1 plus the 2 times cosine of theta. So let's do 1 plus 2 times the cosine of theta. That's also going to be kind of the same deal. Symmetry, x-axis, ratio, 1/2, positive cosine. So that means we move right. A minus B is -1. A plus B is 3. A is equal to 1. So drawing our limicon, we would have a point at 0, -1, 0, +1, 1, 0, 1, 3, and drawing our limicon, we could create a limicon that looks as such. It's not perfect to our graph, but as you can see, it matches up based on the ratios. This is 1, 1, 2, 3, 4, 1, 2, 3, 4. So 1 minus 2 times the sine of theta. It follows the exact same pattern. A point here, a point here, a point here, and a point here, and we draw our limicon. Symmetry, y-axis, ratio of a to b, 1 over 2, negative sign, which means move down, a minus b is 3. A plus b is negative 1. Negative 1, you're facing up, but you move down 1, so you're also going down. And then a is equal to 1 going across left to right. So that is the limicon section. Rose curves is the next section. So with rose curves take the form r is equal to a times the cosine of n times theta, and r is equal to a times the sine times n times theta. For when n is greater than 2, if n is odd, there will be n petals. If n is even, expect 2n petals. Let's look at some examples here. R is equal to 2 times the cosine of 3 theta, because we have cosine. Our symmetry will be at the x-axis or the polar axis. Our n, well, here our n value is 3. So we have our n is odd, and we have 3 petals. All right? So when we have 3 petals, we can do this analysis. There are 360 degrees in a circle, or 2 pi radians. But let's do 360 degrees. 360 degrees divided by 3 is going to be equal to 120 degrees. So that means a is equal to 2. Remember, a is equal to 2. The petal length is on the x-axis. With that being said, we're going to go up, so we move 2. So 2 units right here. So that's 1 petal, okay? The next petal is going to be 120, its center is going to be 120 degrees away. All right, so if this is 30, 45, 60, 90, 120, petal is going to be centered around this point right here. It's going to have a length of 2. So it should have a length of 2, and we have our petal, and then our next petal is going to be 120, so we move 60 here, and then 60 here, so the petal will be the length of 2 here. We'll have our petal. And so we have our petal centered around 120 degree increments. And then after that, we can use our calculator to graph and get a better understanding of what this will look like. So we can do graphing. R is equal to 2 times the cosine of 3 times theta. And this gives us our petal curve. Let's graph the next problem. R is going to be equal to 3 times the sine of 5 theta. Right, that gives us a 5 petals, right? And that will make sense. Our symmetry is the y-axis. Our n is odd. Our petal length number is 5. 360 divided by 5, that's going to be equal to 72 degrees. Alright, and A is equal to 3, which is our petal length on y-axis. So we go 1, 2, 3. One, two, three, and I'm kind of, it's hard to guesstimate 72 degrees, so I'm just trying to approximate where the petals would go. And there you go. For C, R is equal to 3 times the cosine of 4 theta. You have a symmetry across the pole and the pole, which is going to be the origin, in addition to the x and y axes. So let's look at a full symmetrical petal. Our n value is even, and our petals have the value of 8. When we are fully symmetrical, we will have 360 divided by 8, that's going to be 45 degrees. And A is equal to 3, and that is our petal length. Petal length, and because we have 45 degree increments, that's going to be a petal length on all axes and at 45 degree increments. So let's graph this. Clearing annotations. R is going to be equal to 3 times the cosine of 4 theta. That's going to give us a value where we go out 3 here, and we make our graph our petal. We go out 45, 1, 2, 3, and create our petal. 1, 2, 3. We have our petal. 1, 2, 3. We have a 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 petal. 1, 2, 3. 1, 2, 3. A petal. Alright. R is equal to 4 times the sine of 2 theta. Symmetry among the origin alright, the x-axis and the y-axis. Our n is even. Our petals, we have 4 petals. 360 divided by 4 is equal to 90. So we just have our A value is 4, and our petal length is going to be 2 theta equals 90. Theta is equal to 45 degrees. So when we graph our petals now, we're going to go out 4, and we're going to be actually on the 45 degree line. So we're going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4 units. Then you draw your petals. So we've drawn our petals, and we can verify that our graph is correct by using our calculator. Y is equal to 4 times the sine of 2 theta. Graph it. And you see that's what the shape is going to look like. Alright, let's continue. Zeros and maximum R values. So example 5 is just finding the zeros of some polar graphs. So R is equal to 16 times the sine of R squared is equal to the sine of 16 times the sine of 2 theta. And so in order to get polar graphs usually using the form R. So because of that, we can find R. If R squared is equal to 16 times the sine of 2 theta, R is equal to the square root of 16 times the sine of 2 theta. And R is going to be equal to, we can bring out the square root of 16 is 4. 4 times the square root of the sine of 2 theta. Alright? And so this is going to be a figure 8. Alright, so graphing this value, graphing this equation, if you have 4 times the square root of the sine of 2 theta, it's going to give you a figure 8 style equation. So you're going to have a max value of R at 4, because the maximum value of the square root of sine of theta is going to be 1. So the max value of the absolute value of R is going to be 4. So if R is 0, theta is 0. Let's graph this in our calculator. Let's do our delta table. That is going to be equal to pi over 12. And pi over 12 is going to be approximately equal to 0.2618. And the delta and the change in degrees is going to be about 15. So let's look at these values. we go to table set. So our delta table is going to be about pi over 12. And then looking at some of our values, we go to the table. Let's start our table at 0. Alright. So we definitely have 0 and 0, and then we also have when theta is pi over 2, that's when we are plus or minus 2.83. So zeros will occur at 0, pi over 2, and pi. The best way I can explain on why these zeros occur is that when you try to look at when the values on the graph are 0 and try plugging it into the equation for these common values. Alright, so we also have a symmetry test. For our symmetry test, remember we have values at 2.83 pi over 12 and negative 2.83 pi over 12. If we can draw this correctly, it is at these values. We have 2.83 comma pi over 12 and negative 2.83 comma pi over 12. And this is based on, look, if we go to our table value, about 2 point, if we have move up 1 pi over 12, our R value is about 2.83. So this is just an example of showing some symmetry here. Clearing annotations, let me mix this up. So at the end of the day, the main thing you have to do is graph your equations. One last thing I want to do is the logarithmic spiral, and when you graph your logarithmic spiral, it's going to be r is equal to theta over e to the 4th. Alright, you can also write it as 0 is equal to theta is equal to 4 times the natural log of r. So plotting these values, if you plug in these points, this will give you 0.308, this will give you 0.456, this will give you 0.675, 0.822, 1, 1.48, 2.19, and 3.45. If you actually go through the process of graphing this meticulously, you will find that, well, you can put some critical points like 0, 1, but that you will constantly rotate inwards in this direction and start rotating outwards. So that 2.19 and as such. So you're always rotating inwards and outwards. Notice r is possible for all theta, so also as theta approaches negative infinity, r will approach 0, and as theta approaches infinity, r is going to approach infinity. Is there any symmetry? So as far as their symmetry, the spiral moves infinitely. So the main takeaway is the spiral will move infinitely towards the pole, or towards the pole when moving clockwise. And away from the pole where the pole is the origin. When moving counterclockwise. Alright, that is your video. I hope you have a great day.